everyone. Welcome to the Introducing RSPile Maintenance Plus webinar. We're here today to talk about the pile analysis software from Rocscience, RSPile. We're going to talk about the new features of the program that were released with Maintenance Plus, and also all the applications that you can use RSPile. So let's get started. And if you have any questions at any point of this presentation, you can type in the question box that you can find in your GoToWebinar meeting manager, and we're gonna respond on the go. First, let's start introducing ourselves. So I am Clarissa Aguiar. I'm a professional engineer in Ontario, and I work as a geotechnical sales engineer at Rocscience, where I'm responsible for the North American market, and I have experience with pile as a consultant in Brazil and also in Canada. And I have here today with me Dr. Ahmed Mufti. Dr. Ahmed Mufti is a professional engineer in Ontario as well, and he's one of our geomechanics specialists, and he's our pile expert. A little introduction about Rocscience, who we are. So we are a Canadian company located in downtown Toronto, and we develop software for over 20 years. We have nowadays 16 software, and we are developing even more. And we started as a group of research at U of T, and nowadays we are over 50 employees. Just before we get to start with the software applications, the software features, I'll have Dr. Mufti talking about piles, so a little bit of theory before we get started into the software. So please, Dr. Mufti, it's your turn.
Thank you, Clarissa, and I'm welcoming everybody here. I'm glad to be with you, professionals and pile engineers. You are most probably familiar with the requirements of pile design and piling engineering. We are going to talk about the piles and common uses of piles and how RSPile, our software, can handle the usual daily life of a piling engineer in design and analysis. Piles are deep foundation elements that are driven or installed by drilling into the foundation soils and rocks to transfer the structural loads from the superstructure to deeper ground layers. And the advantages of using piles can be summarized in obtaining high bearing capacity, substituting large areas required by shallow foundations, spreading the loads at deeper depths, leading to cost savings. Piles will present better stability and produce less settlement. Piles usually used to transfer loads through poor soils into rock beds or harder soils. Piles may be frictional in nature, with the strength increasing along the pile with depth. So soft clays, for example, at the top, with the stiffer clays at the bottom. Piles may be used as groups under pile caps, and they work as one unit to support the applied superstructural loads. Piles may be used in offshore structures, with part of the piles overhanging above the seabed or the soil ground surface. Then part of the pile will be submerged in water. Piles may be used to support sheet piles, maybe supporting retaining walls. Some will be inclined batter piles. And piles are also used to support an overturning structures or structures subject to overturning loads. So some of the piles will be in tension and other piles will be in compression. There are many other uses of piles, but let's not detail this part too much. We just want to see how RSPile can be used to handle all kinds of pile analysis and design. Pile types are usually, piles may be usually divided into displacement piles and replacement piles. The displacement piles may be large displacement piles like driven piles, precast piles, timber piles, closed-end pipes. They may be circular or box-shaped, filled with concrete or plain concrete or reinforced concrete and unfilled. While small displacement piles, they don't displace the soil too much as the large displacement piles. These are usually driven piles made of thin-walled sections like H-beams, I-beams, or open-ended pipes, whether circular in shape or box in shape. On the other hand, we have replacement piles, and the replacement piles are usually reinforced concrete piles, or sometimes even plain concrete piles. They're drilled piles using a casing, which may be a permanent casing, remains there in the ground with the pile, or maybe temporary, driven out after casting. The drilling usually can be done under drilling fluid like water, polymer, or bentonite, and may be in dry conditions. One kind of replacement piles, which is called continuous flight auger, the CFA piles, are also falling in this category. There are other pile types which are not mentioned in the previous ones, like reinforced mini piles, Franke piles, helical or screw piles, enlarged base piles, under-reamed piles, composite piles, micro piles, and unreinforced bore piles. The common pile applications are usually summarized in the following. Piles may be short piles or long piles. Piles may be subject to lateral loads. Lateral loads may be on an overhanging part of the pile, causing additional moment. The pile head may be fixed, like this one, or free-headed, like this one, or maybe restrained in the middle. What we need to see from our pile analysis are usually bending moment diagrams along the depth, soil pressure along the depth, skin friction, end bearing, resistances of the pile, shear force distribution along the pile. We may need also rotation or lateral displacement or vertical displacement of the pile. And of course, any other structural requirement like stiffnesses, like soil reactions. RSPile, as a software for a piling engineer, can handle all these requirements. Piles may be subject to vertical loads and in different geometric shapes. Maybe it will be inclined piles. Maybe the load will be eccentric, so it causes a moment at the pile top. The pile may be overhanging with having a vertical load and a horizontal load, or even mixed with a bending moment. RSPile provides you with a set of predefined soil theories that can be used, but the user can define his own soil model using a given table, a prepared table by the user for TZAT, for QZAT, or for PY curves. Or the user may choose any theoretical model that is well established and commonly used based on his local practical experience. And these models may be changed through the depth for each segment of the pile and based on the soil layers. RSPile can also handle and calculate bearing capacity, carrying capacity of the pile for you. It can count for negative skin friction, a scorable depth at the top, or soft soil that may be ignored, and it can give you the skin friction along the depth and the end bearing at the bottom and the total carrying capacity of the pile. Piles also may be analyzed in groups under a pile cap, which make them having some reductions in their capacity or behavior that you may, as a user, apply some factors for group effects on the lateral behavior of the pile or the vertical behavior of the piles. The groups may be under a pile cap, which is subject to a vertical load, shear load in both directions, and bending moments in either direction or both directions. Pile load tests also may be simulated by RSPile. So you can have a vertical load test, and you can simulate that one with producing a load settlement curve. You can produce a lateral load deflection curve if you have a lateral load test. And with the new features that we have in RSPile, you can simulate even what is called the Ocell load test by applying the loads at any point along the pile, and you can divide the pile into two parts. With this, I can transfer the presentation again back to Clarissa to show you how to model using the RSPile.
Thank you, Mufti. So right now, after we got this introduction and we saw all the applications that are possible with RSPile, we're gonna see how can we do with the software, where can we find all the features that we need for this kind of for the analysis that you're looking to perform. So you have in RSPile. RSPile is a very comprehensive and complete program because it has different applications. So these are the main applications of the program. So it does individual pile analysis, group pile analysis, and it's the only software that integrates as well with a slope stability software, slide 2. So for the individual loaded pile analysis, we have individually loaded pile analysis. It could be a laterally loaded pile or actually loaded pile. And we also have bearing capacity of driven piles. We're gonna talk about each one of them right now. So let's first start with the interface. So in version 2, we redeveloped the software. We added this new interface, which is based on the software Saddle 3, the settlement software from Rocscience, where you can model non-horizontal ground surfaces as you are seeing here, and you can add as many boreholes as you have in your project, defining by thickness or elevation of your layers. And after that, the program will interpolate the layers. There are several methods for interpolation available, and you can plot your pile anywhere here in your model in the plan view, and you automatically will see that in the 3D. So you don't need to worry about interpolating the layers, and you can have more than one pile in a single file, in a file here. So let's start with the driven. So driven is bearing capacity of driven piles. And it's based on the program driven from the Federal Highway Administration, and it shares the same soil properties and pile properties. So for cohesionless soils, we have the friction angle or the SPT, the N values from SPT tests. Or for the cohesive soils, we have alpha methods and also the option to enter your user-defined adhesion. For pile properties, you can have non-tapered piles and tapered piles. And you can find it in the library. And the program also considers if you have a soft compressible soil and scarable soils. And also you can take into consideration the driving strength loss, and that we're gonna see the effect of this that I've just mentioned, these considerations, and the three results considerations that we have here: the restrict, the driving, ultimate. So for the driving, we take into consideration the strength, the driving strength loss. And for the ultimate, we take into consideration the soft compressible soils and scarable soils. You can also see the results by screen friction and bearing or total, as you're seeing here. Everything that I'm going to talk going forward is a different part of the software. So it uses a finite element engine that doesn't require you to mesh. It's a finite element engine that's designed specifically for piles. And right now we're going to talk about single pile analysis. There are loaded piles. So we have, as I mentioned before, laterally loaded piles, and we have actually loaded piles. And with RSPile, you can also do in a single file analysis, you can also do both at the same time. So you can opt to do laterally loaded piles slash actually loaded pile analysis. You can do both at the same time, entering the properties for both. So for the laterally loaded piles, you would need to employ the PY curves that are the relationship between the soil resistance and the pile deflection for lateral deflection, and actually loaded piles which uses the TZ curves and the QZ for the screen friction and the end bearing element respectively. So as I've mentioned, for the lateral pile analysis, we have PY curves, and we have the most comprehensive library of PY curves, as you can see here. And we also have the user-defined option. All these options here, you can find more information in our online help. So there is also reference for you there. And if you're missing anything, just do not hesitate to contact us, and we can add to the software. Same thing for the TZ curves that we have available. We also have the option of user-defined if you want. Pile. So for pile properties, we introduced new stuff here. I'm going to talk about that in the next slide. We already have lots of options for you. We have elastic models, plastic. So reinforced concrete is where you're going to find new features, and pre-stressed concrete. So for the elastic, we already had the typical sections with a bunch of different options of piles that you can find there, huge library. And for the reinforced concrete, it gives you the flexibility to model piles like that with rebars, with casing, core, and with beams. So same for the pre-stressed concrete. And for the reinforced concrete, we added something that was one of the requests from our customers. And now you can limit the depth of your reinforcement. So you can have different patterns and limit the depth, the bottom depth and the top depth of any of these patterns that you have here. Same thing for the casing. You can also limit the length of the casing. New feature alert again. So once you have your pile property set up, you like to add to your pilot loading. So you can have static, cyclic, or LFRD. You can have a load factor profile in your loads. The conditions, there are many. You can add in different directions your load, also moments. And right now you can add this load at any depth. So before you only could apply the load on top of the pile, but right now you can apply anywhere along the depth of your pile, and that would allow you, as Mufti mentioned, to model a Ocell test, let's say, and you can apply the loads at any length of the pile, any depth of the pile. Displacement profile is also another option for you. You can have displacement profile like that, non-uniform, or you can have a uniform displacement profile, and you can use the soil displacement just with the displacement and the sliding depth. Another new feature, so right now you can apply traction to your pile, and it's a distributed load along the length of your pile, so it could be anywhere here along the length of your pile, could be in any direction as well, X, Y, and Z. PY multipliers, so these are important to take into account the battery effects, scale, the group effects, and other errors that you want to take into account. So this is going to modify your existing PY curve, the PY curve that you showed, and you can do that for the TZ curves and also for QZ. And this is the output of the program, and you can see in the background the soil profile, how it looks like in your pile, and you can see results for different results here, as you can see. And the graphs, you can easily export this to Excel. So this is ladder loaded pile results. And you can customize this, and I'm going to show you that right now in my demo. So I chose this demo because with it, I can show you many of the new features of RSPile. So this is what we're going to build. It's an offshore pile submerged, and it has traction, as you can see, along the length of the pile. Also, there is a lateral load, actual load on top of the pile, and it's a fixed pile. And we're going to model that on RSPile right now. So let me show you how easy it is. So this is the model ready. As you can see, we have non-horizontal ground surface. The pile is above ground and is submerged. And these are my results. So let's see how I do this. I'm gonna open here initial file so we can get started. So first things first, I'll go analysis and then project settings. So as I've mentioned, we can do actually and laterally loaded and file analysis in a single file. So I save time with this because I can enter properties for both in the same file. And I'll just hit OK. Another thing I want to show you is that we have also Imperial Units. In this case, for this example, I'm using metric, but you also can opt for Imperial. And as I've mentioned before, we're going to do a submerged pile, and the water table elevation in this case is 3. And I'll leave here as it is. Hit OK. So now let's, after we finish here with analysis, let's move to Soils tab. So here at Soils, I'll start defining the soil properties. And just to save some time, I've already defined the soil properties that I'll use for the 3 layers that I have in this project. And I've defined properties for axial and lateral soil properties. So I also defined unit weight. We have reference values here for you can pick. So we have unit weight and saturated unit weight as well. For the lateral, we have different soil types, as you can see. If you have any questions about any of the soil types, you can click on this question mark, and this will open Rocscience website, online help, and you can check any of the soil. So here the sand, and you can find the PY curve. That's exactly that, and also some reference values. So same thing for actual, so all the options that we have there. And note that I already have set up properties for dense sand and stiff clay. I'll just hit OK here. And next thing in the soils tab would be to use the Borehole Editor. And for this example here, I'm going to use 4 boreholes, as you could see. So I added here 4 boreholes, and now I am going to, I have already some values. I'm just going to copy and paste here some values that I have already for each layer. So let's just define here, and they have to have different coordinates, and I'm entering here the coordinates. And as you can see, they can have different elevations. The ground surface is not horizontal. Okay, so as you can see, I have 4 different boreholes. I can see my soil layer column, how they look different, and they are located at different places. They have different locations here. Clicking on here, this engine here, I can see the borehole settings. I can see interpolation methods that I have available, as you can see, and also you can change the resolution. I'll keep as it is as the default values, and I'll hit OK. And automatically, I see my soil model was created, and I see the water level. Now I need to model my pile. So let's model this pile. I'll click on Pile Properties, and I will select here one pile property, and I'll create my offshore pile. And for this example, I'm going to use the reinforced concrete so I can show you the new features for pile properties. And we're going to use a 1 meter diameter pile with 40 here MPa. And so let's design it. So this is the concrete designer dialog, and I'm going to add 2 patterns for this pile. So the first pattern, I'm going to use here a 25 millimeters bar, 6 bars with cover depth of 100. And I'll keep these values here, the properties as they are. And I'll not limit the length of this one. And then I'll create another one, and I'm going to limit the length to 10 meters. So this pile will have 20 meters long, and this one it's going to be shorter. And note that there is an overlap here. I can visualize that. Just to change that, I am gonna need to change the angle, and I'm gonna need to change here for 25. So I want to use the same reverse. Okay. So there's no more overlap, and this second pattern is not as long as the first one. Okay. So for the casing, I can also limit the length, and that's what I'm going to do. I'm going to create a 25 millimeters casing, and I'm going to limit the length of this casing to 9 meters. I'm going to also change the stress here, and I think it's all good. Good. Okay, so I created this offshore pile test, and I'll hit OK, and nothing happens because now I need to add the pile. So I'll go Pile and then click Add a Pile. And now I can select the property that I'm going to use. So I'm using this offshore pile test here. And I'm going to start with the geometry of my pile. So as I've mentioned, it's a 20-meter long pile. And the elevation of this pile, it's 5. So it's above ground, 5 meters, as you can see here in the presentation. And I'm going to add now the loading. So let's add here loading. And I'm going to add a the direction will be general. And let's see here what I need to add again. Actual load to in the direction X. And I'll add the traction later. And I'll also make the pile rigid. So I'll put a very high number value for rotation in Y. So let's add here force in Z, shear in X, and also rotational stiffness in Y. Y I'll have 2 because I want to have a 0 and 1 meter, as I can see here in the picture in the head of the pile. So for the force in Z, that will be on top of the pile, so the depth is 0, and that's going to be minus 150. It's a compression. And for the shear in X, that's going to be 25 at 0 in the top of the pile and 25 at 1 meter at the pile. And then I'll add a huge number here for the rotational stiffness, and this is at 1. The pile is fixed. So after this, I already modeled the point loads on the top of my pile. I'll go for the tractions, and I will model exactly the traction that you see there. It's varying from 6 to 3. So I just click on plus, and I'm adding a new traction. And this traction is going to be in the axis X, and I have 2 lines because it varies 2 times. So it starts with 6, at 1.5 from the top and goes to 4 at 4.5 from the top, meters from the top. And then from 4 at 4.5 meters from the top, it goes down to 3 at 6 meters from the top. And I'll just hit OK. After that, I just need to add my pile anywhere here in this model, and I know already the location, and I can type here 14, 14. So those are the coordinates, and I'll hit enter, and my pile will be automatically located here in the project. Next step will be to hit the calculator and see how quick it's going to be this analysis. Okay, I already have my results. It's just a couple of seconds, and I can see displacement in X, where the shear force is applied. And then I can see also in Z, because of the actual force, rotation, the beam shear force, actual force, and a bar. But let's see those results in a graph. So I just basically need to click on graph general pile data, or go to graphs, graph pile, and then click on my pile, select my pile, and go enter. After doing that, I can see my results, and I can see also in the table all the data for these graphs. I can change this graph. So let's say I want to also see the actual force. So I'm going to replace here rotation Y with being actual force. I'll hit OK, and I'll make the chart. I'll add the table columns to match with the charts. As you can see this here. You can transfer all this to Excel. Just clicking here on export to Excel. This Excel button. And that will generate a Excel file for you with all these graphs. It's already done. With all these graphs here, so you can do further analysis. So let's go back now to the presentation, because there are also other things that I want to mention about single pile analysis. We have other options on once you're adding the pile. We have other options for advanced analysis. So we also have stiffness matrix calculator, pushover analysis, pile length analysis, and resistance graphs. For the next example here, the next topic I'm going to talk about is the resistance graphs. We're going to be using this for the integration with slide 2. So let's talk about this a little bit. So integration with slide 2, you should be interested to use our this integration if you're using a piles for slope stabilization, because this is going to save you a lot of time. And how it works, if you have a pile being used for slope stabilization, right? So you would increase your safety factor of your project. So what's happening is that there is a slip surface that's cutting this pile, and you want to know if your pile is able to resist to this slip surface and to this displacement. So against this displacement, there will be a resultant force, and RSPile is capable of giving you this resultant force if you have the pile model in RSPile. So what basically you need to do is to select the support as RSPile support, and then select your file. And after you select your file, it's going to ask you to match the soil properties that you have in RSPile with the slide 2 properties. So based on the name of the layers that you have in both programs, you know that interface from Rocscience is really similar between the programs, so it's easy to identify. And after that, you would define the displacement, the maximum displacement, that's the design criteria. And in the interpretation, once you click to see the resistance graph diagram, you can see exactly the force that's been applied on that point, and also along the pile for different sliding depths, as you can see here. And you can export that to Excel from slide 2. But if you want to do further analysis in RSPile, what you can do is use the resistance graph. There are in advanced analysis. So with that, you can plot the resistance, actual and lateral resistance for different soil displacements. You can have a maximum soil displacement, also ultimate soil displacement. So the ultimate is the purple, and the maximum is the red line here, as you can see. So these are results of the resistance for different sliding depths for axial and lateral. And you can also plot different results for different sliding depths. So each line here represents a sliding depth along the depth of the pile. So you can also plot different results here. In this case, I have the actual force. In this case here, I have the displacement in X for the lateral. So now let's move on to group pile analysis. So everything, all the properties, soil properties and pile properties that I've presented, they are shared here with group pile analysis. And there's just a new dialog, which is the cap designer. So right now, instead of adding the pile, you are adding the piles in a cap. So you're putting them in this group. So first things, first you would model the shape of your cap. You can define different shapes. Then you define the patterns of your piles in the cap. So you can have different patterns. You can have customized patterns. And then you add a load. So you can add the load in the middle of your cap, as you can see here, but you can have more than one load anywhere in your pile. And we also have LFRD and cyclic load, same as individual pile analysis. Connectivity, you can set the connectivity of each one of the piles as fixed, pin or restrained. And in the advanced tab here, you can define different lengths and elevations for your piles. You can define different orientations, as you can see on this 3D view here. You can define different displacements. Multipliers can have different multiplier curves for different piles. And you can opt to use group effect. So we have the automatic calculation for the lateral effect. You can opt to manually enter these values or ignore the lateral effect. The actual coefficient is always up to you to enter. And this is the output, and looks how nice it looks, because you can compare different results of different piles. And you can also export this to Excel and much more. So right now, I'm going to pass the presentation to Dr. Mufti, because he's going to talk about a study that he was involved during design phase. It's the case study of a silo foundation. And this, if you can find this study at our Rock News, in our website at www.rocscience.com/rocknews. And there you can find this case study and many others where you have the application of our software, how we use our software, and the results explained to you. So please, Dr. Mufti, it's your turn now.
Thank you, Clarissa. As Clarissa said, you can follow up what Rocscience news as soon as published by subscribing to Rocscience News. I think that will be beneficial for you. And welcome back. I'll talk here about a case study of a real practical silo foundation that has been constructed. And the silo is a very high cylindrical one, having a 38 meters height. And the silo foundation was a pile cap of 28 meters in diameter. And this pile cap was supported by piles. So here is the basic modeling steps, we shall go through the project settings, as Clarissa explained just a little bit ago. So we will talk about the soil properties, then the pile properties, and define the pile cap. Then we will apply the loading and the pile patterns and the pile connectivities to the pile cap, and define the pile lengths and orientation, apply the group effects, and compute and get our results. So in RSPile, you can see a very interesting shapes or pictures of the forces and results, whether they're displacements or soil stiffness or reactions. Let us go to the modeling, and we will model this pile cap and see how this silo foundation will be analyzed. To start, we assume the circular pile cap having 4 patterns of piles. Each pattern has a circular ring of piles, and these patterns can be defined in piles, as we will see. So we will start with the project settings. Then we will choose group pile analysis. Then we go and define our soils. And we have 2 layers or 2 types of soils here. Then we go again to soils and define our borehole, the thickness of the layers in the borehole. We have only 1 borehole here. You can apply more boreholes if you have. Then we define the piles through the pile cap or the pile group with cap. We will see here, first you define the shape, whether circular or rectangular or any custom shape you want. Then you put the thickness and the diameter. Then I'll go to the patterns, and I choose, see, 4 patterns here, a pattern for each ring of piles. The inner ring is pattern 1, then pattern 2, you can see here, and pattern 3, then pattern 4. As a first trial, I defined the pile type as a trial pile. I'll show you how to define the pile types. You will come here and see the pile properties. I have the trial pile, and later on, you will see how I will change the pile patterns into other 4 types. So the trial pile has 1 meter in diameter, and the whole number of piles, they all have, you can see here, edit pile properties or edit cap design. In cap design, you need here in the patterns to show the pile length. So pile length is 15 meters, and the number of the piles in pattern 1, 8. Then we distribute them by distance from center and by angle from x-axis. So by the number and the angle and the distance, the program will distribute the piles for you. For example, another pattern like pattern 3, there are 16 piles, and the distance from the center, I gave it as 8.4 meters, and the pile length is still 15 meters, and the trial pile is the same trial pile that I used. See, for example, the design of the trial pile. I can give a reinforcement pattern and the diameter and the concrete strength and the yield strength of the steel, the elastic modulus and number of bars and the cover depth and the type of the bars and the types of the distribution, whether radial, rectangular, custom. Of course, here we have a circular pile, so most probably I will use the radial distribution. And here the concrete strength. After defining the patterns of the pile, I'll define the loads. So this silo is a huge silo and has a very high load of 24,000 tons, 240,000 kilonewtons downward. And because of wind load and seismic load, we may have a bending moment or a moment at the pile cap of around 110,000 tons meters or 1,100,000 kilonewton meters. And additional horizontal force that is around 10% of the vertical load. These values are input here, and you can distribute them anywhere you want on the pile cap, or you can lump them in the middle as you have the application. The pile cap will be analyzed for all applied loads in one run. I need to define the connectivity of the piles to the pile cap, so I will choose fixed here. I can choose pinned or restrained. If I choose restrained, I need to define how much is the restraining stiffness. But in our case, the piles were assumed fixed, as the pile diameters compared to the pile cap stiffness were small. And if I go to the last tab, which is advanced, I can see here, I can choose length and elevation and change any length or elevation of a pile, of a single pile within the group. I can change the orientation of these piles. I can change I can define a pre-applied displacement. I can have the multipliers on a TZ or a PY curves. I can apply the group effect. So I can have the axial group effect. I can put any figures I want. Usually the axial coefficient is close to unity because of the enough spacing given to the piles. But the lateral effect, you may choose automatic, or you can choose manual, so it will give you another column to add your own values. After finalizing all these steps, I'll have the silo pile cap and its piles layout ready to be analyzed. My concern, usually, because I have a shear force in X direction, a vertical load in the middle, and the bending moment. So the worst piles will be, for me, to consider them in the design, will be pile 1, pile 9, and pile 25, and pile 41, which are defining the piles of the 4 patterns, respectively. So I will see the results of these piles after I run, and I'll choose these piles, and I'll have a look to the results. This is the preliminary design, so I will see the results here. I can change and edit the charts. I'll choose the axial force and take it as second graph. I don't need these stiffnesses or soil reactions. And I see my piles now. They're having, these are the 4 piles, and they're having different loads. As the loads on the piles are different, of course, this is due to the moment and the shear applied at the top of the pile cap. I don't need to keep the piles all in the same length and same diameter. So I'll choose different diameters and different lengths for these different loads. So with a couple of trials, I can find out what should be my final layout. So I chose 1.2 meters diameter for the outer ring, 0.8 meters for the inner 2 rings, and 1 meter diameter for the third ring, with different lengths. The first length is 7 meters, 9 meters, 15 meters, and 24 meters. And after I made this layout, it's very easy to change this. As soon as I go to edit pile cap and I go to pattern and I choose pattern 1, I just change the pile type from the trial to the pile type I want, pile type 1 with a pile type 4, and I'll get a new pattern. And I change the length accordingly. And you can see the pattern is defined already as 0.8 meter in diameter, and the design is completely different. The 800 millimeters have different number of bars, corresponding to the load that I have found in the first preliminary estimate. And the same I do for the pattern 2 and pattern, sorry, for pattern 2 here and pattern 3. You can see each pattern have its own pile type. Then I go and define the loading. The same loading is here. Then I define the connectivity. Then I press OK. I can now run the program and get the loads again on these piles. I'll choose pile 1, 9, 25, and 41, and have a look to the load distribution again. So I'll edit the charts again. I want axial force distribution. Take it up and remove this one and this one. So I have a new distribution for the loads on the pile rings. The first ring has a small load, and the loads we obtained this time are 2,500 kilonewtons, 3,600 kilonewtons, 6,400 kilonewtons, and 11,100 kilonewtons. These loads are adequate and comparable with the pile capacities. How do I know that? I made another run choosing different piles, different diameters and lengths. So these are pile type A, B, C, and D, respectively with the rings, pile rings in the pile layout. And I made a couple of piles, repeated them, and each pile here, from pile 1 to pile 9, for the same type, they have different loads. So this one, for example, has a load of 8,000 kilonewton, while this one, for example, has a load of 2,500 kilonewtons. I chose these loads to cover the capacity and the load settlement behavior of this pile. I'll do a full run of these piles. So I'll see the results of these piles all in one shot. And I see all the load settlement for each displacement. I have the beam axial force, and I can send all these and export them to a data Excel file. And I'll see something like this. So for each pile, I have loads. See this load for all the piles. Then I choose the 4 piles in question that I am interested with and get their loads with their settlements. And I'll obtain the load settlement curves. From the load settlement curves, I can get the pile carrying capacity, and I will get from that the factors of safety for these piles. Let's go back to the presentation and I'll show you how can I obtain these load settlement curves. So here you can see the results. Each pile type and its graph generated from those many piles that I have analyzed. And each point here corresponds to a single load on that pile. So I have the load and the settlement. I can construct the load settlement curve of that pile type. And by any method, like the method of tangents, I can get the pile capacity. This pile carrying capacity divided by the applied load obtained from the analysis, I can get the factors of safety. So I have these graphs for the 4 types of piles, and I can get accordingly my factors of safety. If you want to know more about the study, you can go back to, you can refer to the Roc News, and we are also available for any questions. Thank you. I'll go back. We will go back now to Clarissa.
Thank you, Mufti. Just before we go to the questions, I want to make a recap here what we presented today. So today we talked about the main applications of RSPile. We talked about single pile analysis for driven, actually and laterally loaded pile analysis. We had a demo featuring with the new features of RSPile that were introduced with Maintenance Plus, such as that you can add a load at different depths, and the traction, and also the reinforced concrete dialog that allows you to limit the length of your casing and rebars. After that, we talked about integration with slide 2, which is a very unique feature, and then we covered the group pile analysis, and finally we had a case study with Dr. Mufti. So we're gonna answer all your questions and get back to you individually. And if you have any questions, please do not hesitate to contact us in our email address, as you can see here on the screen. Upcoming webinars, there will be new webinars coming up soon for Saddle 3, EX3, and Slide 2 with the new features of the software that are coming up with Maintenance Plus versions of them. And I would like to thank you so much to attending this webinar, to watching us today. Please don't forget to follow us on LinkedIn, Twitter, Facebook, and YouTube, where we're regularly posting new stuff for you. There are articles, case studies, webinars, workshops, and much more. So stay tuned, and thank you so much for your attendance today.
Thank you.